Hello, everyone, and welcome to our midterm project presentation on content-based image retrieval, or CBIR for short. My name is Nguyen, and today my partner and I will show you how we designed and implemented a CBIR framework in MATLAB. And then our project explores how we can search for images by example, like using the image itself as a query, instead of relying on keywords for our searches. Now, here's a brief overview of our presentation. We'll start with some background information on the content-based image retrieval, what it is and why it matters. Then we'll move into a short literature review highlighting some common features like color, texture, and shape. And then next we'll describe our method, which includes how we implemented CBIR in MATLAB. After that, we'll share some experimental results and retrieval examples. And then finally, we'll wrap up with a conclusion, future improvements, and references, followed by a live demo of our framework. Now, here's a simple overview of what CBIR does. Now, instead of searching for text or keywords, the system takes a query image. So, on the top right-hand corner, we have the tree as the example. So, what it will look at is things like color, texture, or shape, and then capture all of these as a feature. Then the system will compare it to those features against the database of images. And then the goal of it at the end is to return any visually similar results, even if they don't have the same file name or text tags. This makes CBIR much more powerful for cases when we're trying to search for large image libraries, like medical scans or even e-commerce catalog. So another big question is, why do we need CBIR in the first place? Well, the main reason is that not all of the images are annotated to the same way. For example, that like a large collection of images, like for example, medical scans or say satellite images, there may be no consistent metadata at all. So using traditional search key search words only works if images are labeled properly, but reality sometimes the people who put in those images they might not put it accurately or they might mistype something. And then if there's a large number of these images, then it might be too difficult or sometimes even impossible to locate the actual image. So utilizing CBIR, it's it helps because it can be accurate and faster because instead of searching, I want this specific tree or I want this specific animal, it'll look at the image and then it'll find all of the images within its database or compare it against its own database to find which is similar to that. And then now let's look at the three core types of features that CBIR relies on, which are color, texture, as well as shape. So a color histogram, like the ones that we have implemented, it captures how often a specific color will appear in an image. And then this even works even if the image gets rotated. And then another feature that we look at, or that it looks at, is texture, which will describe any patterns like smooth versus a rough surface. And then it can help through local binary patterns. And then looking at the shape of it as well, the shape will look at the edge detectors or looking at the geometry of the shape. And then these can be powerful because it requires some pre-processing, but it also can segment the image as well, and then it can differentiate which actual shape that it's trying to look at as well. But then overall, looking at what the edge detector does, and then all of these, they don't work individually, they all work in unison together to ensure that the color matches up as well as the texture, and then the shape, they all match up together within that image. Now let's look at this next diagram. So in this one, it's a more descriptive overview of what the CBIR framework actually looks like. So we have on the bottom left-hand corner, we have the snowy, almost like a snowy, blizzardy like image. And this is our request image or the request query. So then a few things that it will look at is, oh, the color of the sky or the shape of the leaves or the color of the snow in the background. So I'll capture these features and then calculate it within the metadata, and then looking at a large image database of other ones that will have, say, a tree or like a dog, just a bunch of different images within it. So it'll calculate those features within its own metadata, and then it will store it within its own database. And then as we try to compare it with ours, then it'll be, oh, this one is a tree, or this one is similar to a tree, and this one's similar to a tree. So let's narrow it down. Oh, it has snow in the background, so let's go find a snow image or a tree with snow in the background. That's where it compares against each other. And then that's why on the right hand side, we can see that two of the images match up or have a similar background where it's like a snowy background, and then the white trees as well. And then I'll pass it off to my partner who will go over the results and conduct a live demo at the end as well.
So in terms of how color-based, content-based image retrieval is implemented in our code, the first step involves building a database. So encoding every image that you want to be in your database to a 6-bit color code, taking the color histogram of all of those 6-bit images, and then normalizing each one of them. The reason you want to normalize it is so that the size of each image doesn't contribute to how well it's matched, right? If we have an image that is large and a pretty much identical image that is small, we would like those to be matched to each other. After you've built your database, the next step is actually just retrieving your image, which first involves processing the query image, so the image that you want to compare and get similar images to, which involves coding into 6-bit and then getting its normalized color histogram. Once you have the query image processed like that, you can find the Euclidean distance between the query image and every image in your database, which essentially follows comparing the intensities in each of the query images histogram bins and every database image's histogram bins, finding the differences, squaring all the differences, adding together in square root the equation that's shown on the screen. And then after we have the Euclidean distance between the query image and every database image, we want to return the top 20 ranked images with the lowest Euclidean distance between them and the query image. So in other words, the images that have the lowest Euclidean distance are most similar to a ranked image in terms of their color, their 6-bit color histogram. So in terms of results from our implemented methods, what we get when we put in the following image 101 is we obtain the 9 images that are in our database that are roughly identical to our query image, which is exactly what we'd expect from the system, right? This is a very good result. It's very good that we're able to recall images that are roughly identical to our query image. And then we see in the later ones, we have images that are green, images that are kind of blue, which are also retrieved, ones that are not exactly what our query image is, but might have a similar color profile. One thing that's a bit unexpected is that all of our dark green images aren't together. They're kind of split in the middle by these cityscapes. And so that could point to there being some limitations in our code. But as for the recallability of our code, it's very demonstrably very good. In terms of another example that really highlights how good at recall it is, we saw a query image 21. Using that, we're able to really easily recall 2 images that are identical to the image. And then we're able to recall 286 and 287, which are almost identical to the image, after we recall the identical ones. So that also demonstrates how good our system is at differentiating between images that are similar but not exactly the same as the query image. And then after those 4 very similar images, we get a bunch of images that are mostly white, just because they fit the color background of the query image. Numerically, the recallability in both of our cases was really good. We had perfect recall. Every single identical image was recalled. Every single image that was very close but not quite identical was recalled after the identical ones. In terms of precision, though, it's a little bit lower, and the reason for that is just because we did not consider at all how close to the query image they were, just whether they were in the top 20. So, the 20th image isn't necessarily particularly close to the query image, It's just closer than, the top 21 to 100 images are. And so that could point to some potential future improvements that we could make in order to improve the precision of our system in identifying only images that are really close to the query image. To kind of conclude in terms of advantages and disadvantages, as I was talking about before, our system's clearly very good at finding identical images and clearly very good at discerning between small differences between images. And then in the lower ranked similar images, it can also find similarly colored images, although not necessarily images that look very similar to our query image. In terms of disadvantages, as we saw in case 1, in terms of the less similar images, sometimes they can be ordered in ways that are not intuitive to what we would have expected, and then it returns the 20 most similar images, right? As I was saying before, the 20th most similar image is not necessarily something we would want to recall, or in a different kind of data set, maybe the 22nd most similar image is something we want to recall. And so that could lead to there being things we could improve in the future. And then the other thing that can be an issue is that if you have images that have different contrast or have different saturation in your query image, they can sometimes give false negatives or false positives when they're retrieved. So in terms of future improvements, as I've been speaking about, one major disadvantage of color-based CBIR programs in general is that they don't include any spatial resolution. And so one way to address this could be segmenting images and comparing the subsections of each image, their color histogram to the color histogram of the subsections of the query image in order to get a little bit of that spatial information back. And then the other thing I was talking about is instead of just recalling the top 20, maybe we want to recall images that are only so similar to the query image, in which case it might make more sense to allow the user to specify a similarity cutoff, so anything that is at least this similar is retrieved, anything that is not this similar is not retrieved, which could give users more flexibility in terms of being able to recall, images that have their desired level of similarity to the query image, not necessarily just the top ranked ones. Other improvements we could make possibly going forward is experiment with different distance formulas to try to obtain more intuitive, predictable results for lower similarity images, which was an issue we saw in case 1, and then also possibly experiment with higher frequency resolution images, so perhaps higher than 6-bit, to see if that improves our precision or recallability at all. So here are the references that we used for this talk, and now I'm going to go through a short demo of our code. Alright, so the first part of our code involved making the database, right? So we import all of our images that we wish to be in our database. We read all those images. We convert them all to 6-bit. We get their normalized histogram, and then we add their histogram to our database. And that's honestly the longest computational part of this thing. Once you have the database, it only takes a couple seconds to retrieve anything from it. And so if we go to our retrieval program, after we've already made the database, we will get our image from the user, the query image, and then we will compare that query image's processed, normalized 6-bit color histogram to those of every single image in our database, which are stored in our database variable. After we've done that, we can sort our list of those Euclidean distances in order to find the top 20 images that have the lowest Euclidean distance from our query image. And then we can save those images' names and display them all. So to give a quick demonstration of how that works in this program, I would click Run. The program would prompt the user to choose an image. So I'm just going to go to Import, my import file, which contains every image in my database, and I'm going to pick a random image, and I'm going to open it. And you see it takes a couple seconds, but pretty quickly it is immediately retrieved because I already have all of these things saved in my color histogram. And so, saved in my database. And so we can see already that this is very good at retrieving all of these. So that's a quick demonstration of our code. Hopefully that was helpful.